All right. So before we get going, just a couple things to kind of close out, just logistically about the exam before we kind of dive into review. So we will be in this room next Tuesday, right? So the 16th from 12:40 to 2:40 p.m. Exam length will be pretty similar to that practice final, about 25 questions, depending on how you count them. A couple of them have parts A and B, but about 8 minutes per question if you figure over a 2-hour exam with 25 questions. So, if I'm studying, I try to kind of reiterate this, but the procedure or the steps I would do, I would first review that practice exam. You have the answers, but I would try to be able to provide a solution or kind of be able to reason through why the correct answer is what it is for every single problem, right? I would also kind of then take a look at old quiz questions, especially the ones you got wrong. I would then review old practice problems. I would also, if you then are still looking for things, even going through those old problem sets from Stata, even though like the coding part won't be as important, the questions where there was like short answer responses, like based off of the output, those would be maybe helpful to go through. So you kind of have those do files, you can rerun that my code, see what the Stata output looks like, and then see what the corresponding answer would be. All right. So I put up problem set 6. I put the answer key up there this morning. So due date was yesterday. Started grading a few of those. Hopefully, with the help of my TA, I'll get those graded relatively quick. I'll be working on them a pretty good amount tomorrow. I don't know if they'll all be graded tomorrow, but definitely by Monday, those should all be graded, and you should have those scores so that you would then know what your exam score is going to be. Here, I can even add this. I know it's under the Files tab, but maybe I'll make it easier for you guys to find. Right? Where you can kind of take that Excel file. After that problem set 6 is graded, you know what your score is going to be from Canvas in each one of these categories. You then can kind of plug in hypothetical grades for the final, and it would tell you what your final score in the class would be. Okay. So right now, you have a pretty good idea, kind of based off of your previous problem set average, what your quiz and your in-class quiz score is, and then your midterm, you can kind of play around with that, thinking about what you need on the final to get whatever your desired grade is in the class, right? Other than that, one thing that I did not mention Tuesday, which someone asked me about, so I'm glad they did, which I edited the announcement just to make sure this was clear. So you have that formula sheet, right? As we're working through things, we probably can see like we're not, the formula sheet is in kind of general terms, right? So like even when it says like beta 1 and beta 2, that doesn't mean you can directly apply that to any problem, right? Because I can change the order of where the variable you're looking at is, and it might be the 4th or 5th variable, right? So the way in which it's written, it's as though you're looking at like a squared model where the variable is the linear term is first and the squared term is second. There might be additional controls in there. So that formula sheet is helpful, but what I'm also going to let you do is basically have a one-sided handwritten cheat sheet that you can use on the final. Okay? So as you're kind of studying, you're taking notes, you can write down anything that you want to on this form or on this cheat sheet. All right. It has to be handwritten. So this isn't like, put it into Word and ChatGPT and font size 8 and print it out on a, right? They need to be handwritten kind of as you're kind of going through preparing for the final. But I think this will be helpful, right? Especially if there's things that kind of keep tripping you up. I would make sure I include those on that sheet, right? Yeah.
Your regular size.
Just an 8 by 11 blank sheet of paper. Yep. Okay. Any questions about other questions on that? Okay. So the only other thing that you can have out for the exam is something to write with and a calculator, right? To make some of these, hopefully nothing too crazy in math, but it might be helpful time-wise just to have a calculator with you. Okay. Any other questions logistically about the exam before we keep moving? Yeah. Am I going to ask you for any code on the exam? No, right? This practice final looks very similar to the final in the sense of it's different problems, different variables, different questions. But in terms of format, I'm giving you a lot of output from Stata, and you're really just kind of using that to answer questions. I'm not going to ask you for specific code, right? That's more of just memorization stuff. That's, I want you to kind of understand the concepts behind what the output is telling us. Okay. Any other logistical questions before we dive into kind of working through some review here? Also, I don't know, other professors are different. I get this more with my freshmen, but like once you're done with the final, you don't have to sit for the whole time. As soon as you're done and you hand it in, you can leave the room, right? Now, if you think you're going to take a lot of the time, it might be helpful then to kind of sit in the middle or the end of rows here in this room so you're not getting disrupted. Also, as you turn it in, I will need you to have your crimson card, all right, whether that's like a physical or you can pull it up on your phone once you hand it exam. Don't have your phone out during the exam. But I will kind of be checking those as you turn the exam in. Okay. Other than that, I think that should kind of cover all the logistics. Any other questions for me before we start looking at some of these problems here? Okay. All right. So any questions that people had where they wanted to start out with here?
Would you be able to go over questions?
So we are looking at trying to predict rent and income. We are looking at, okay. So let's start to kind of think about these log linear, linear log, log models, right? I would probably give you some additional information here. I think based off of these variables, I think we can assume some things and you'll see as we work through it, but I'll mention what I might give you as some additional information on the exam. So we started out with a log linear regression, right? So if I'm trying to predict, no, we didn't. We started out with a, linear log model. Looks something like this. And here it was average income, but just to make it easier, we'll kind of write this as income, right? So how would I interpret beta 1? Right? So the general form, if I've got kind of this linear log model, when I take the natural log, essentially what does that change the units of this x variable to? Percentages, right? So if I'm thinking about this is now a 1% change in income is going to cause the predicted value of rent to go up or down by beta 1. However, if I'm going from a percentage to a linear term, I said you can think of linear terms as what? Not percentages, but proportions or probabilities, right? So if I'm going from percentage to a kind of proportion or probability, what would I need to do to convert a percentage into kind of a proportion or probability? 90% is 0.9. So what are you doing there? You're taking whatever beta 1 is and you're dividing it by 100, right? So a 1% change in income would cause a beta 1 over 100 unit change in your y variable, okay? So any questions? I think that was the question 6 was basically to interpret that. And there was an actual value. This would be what? 296. So there we would say what? 2.96 was the change. Okay. And rent is in, I think it was told to be in dollars, right? Now, if I instead run a log linear, right? I take the natural log. Oh, no, this one I actually ask you to run a log model. I take the natural log of both. Well, this almost becomes easier if I was to ask you to interpret the coefficient. Because if I ask you to interpret the coefficient and I've taken the natural log of both of these, what does the interpretation become? It's a 1% change in income would cause my predicted rent to change by beta 1%, right? Or however you want to change by beta 1% here in rent. I don't have to do any conversion. Everything's in terms of percentages when I take the natural log of both sides, okay? Now, if I were to run this log model, here I had a 1% change in income. Here I had a 1% change in income, okay? Its impact on rent, right? This was going to be the effect, right? But I have to then divide it by 100, okay? So 2.96 doesn't seem like a large increase in rent, right? What would likely be true about the percentage change that I would see from that same 1% change, right? 2.96 I'm looking at this right? So I'm going, oh no. Yeah, it was 2.96. So the actual coefficient estimate I saw was 296, right? But the actual effect, I'd have to divide that by 100. So if I'm thinking about things in terms of percentages, do I have to do any type of, do I divide by 100 here? So what's likely going to be true about that coefficient from my log-log model? It's likely going to be quite a bit smaller, right? Because even if I see a $2.96 change in rent, what will that coefficient show up as? 296, right? So anytime I have kind of these linear log models, I'm always dividing that coefficient by 100 to get the actual effect size. So the coefficient itself is always going to be rather large because I have to then divide it by 100 to kind of put it in terms of the units of y. Now I'm thinking about percentage changes here. I don't have to do any conversion. So the coefficient estimate I see is the actual percentage change. I don't scale it at all. So it's likely I'm going to probably be seeing quite a bit smaller of a coefficient there, right? Because it's not going to be getting divided by 100. Now, I would probably tell you something on the exam like, oh, I don't know. I probably would give you variables where it's very clear that like here, the effect of $2.96 seems like a small amount of rent. So it would probably be more likely I give you something where the effect on rent is like more comparable to what a percentage change would be. But here, what I'm really trying to get at with that question is that you know the coefficient estimate you see is not the actual change in y. The actual change in y from your linear log model is that coefficient divided by 100. So what I would probably be more likely to do instead of the log-log model, because it gets kind of weird with percentages, and I could add this as an additional question. So let's say instead I ran what type of model here? This would be a log linear. So I can think about here, the interpretation is a 1 unit change now in income causes my rent or my kind of predicted rent to change by what? Whatever beta 1 is. But if I'm going from a unit to a percentage, how do I turn a probability into a percentage? I would actually multiply by 100. So if I ran this log linear model, the coefficient I see compared to the linear log model is likely going to be quite a bit. So if this is the actual effect, well here, if this is the actual effect when I multiply it by 100, the coefficient I see would actually be quite a bit smaller, right? Because here, the coefficient estimate I see will end up getting multiplied by 100, right? So the actual estimate I see for beta 1 is going to be quite a bit smaller because to convert it into a percentage, I then need to multiply it by 100, okay? Any questions on that idea? Because, right, if this was larger, then what is the change going to be? Like, let's say I saw this was 296. Right, let's just use this thought experiment. If I then run this log linear model, and let's say I see 400, a larger value, what would the actual, and sorry, this was we were converting into a percentage change in rent. What would the actual change in rent be from a 1 unit increase in income, one more dollar? It would be what? For 40,000% change? Does that seem reasonable? No, right? It's likely because we're multiplying by 100, we're probably going to see something more like 0.4, something quite a bit smaller, right? Because we still need to scale it to get that total impact on our predicted y variable, which is now in terms of percentages, okay? So you should be able to make interpretations from any model. Linear are the easy ones. That's stuff before the midterm. But log linear log, and log. Log's easy. There's no scaling. Everything's in terms of percentages. Linear log, we're going from what's the initial thing that's changing x. So if we have a percentage change going to units or percent to a probability, we need to divide that coefficient by 100. If we're going from units to a percentage or probability percent, what do we need to do? Take that coefficient and multiply it by 100. Right? So I would know how to make those interpretations for each of those models. Okay. Any other questions on that one before we keep moving? Just to make another point, since we're talking about these here. So I have here the log linear model, and I ask you to interpret it. But here, let's think about what tells me which model is better. So if I had these two models, I've got a linear log and a log linear, right? What can I actually look at to tell me whether or not which of those models is a better fit for that relationship? Can I use my R squared?
No.
Why can't I use my R squared there?
Because you added an additional variable.
So I didn't add an additional variable, right? How many variables are in both of these regressions? One. It's just a different scaled variable. So even if we don't worry about the R squared, why can't I use the adjusted R squared here? What does the R squared and the adjusted R squared tell you? The percent of the variation that your X variable explains about your Y variable. The percent of the variation in your Y variable that is explained by your X variable. Well, what's going to be true about the variation in rent and the natural log of rent? It's going to be, if I'm taking the natural log of something, I'm automatically changing the amount of variation, right? So I can't compare regressions if they don't have using the adjusted R squared or the R squared, even if I keep the number of variables the same. I can't compare them if the Y variable is different, right? So what are the only models that I can actually compare using my adjusted R squared? Well, I could compare a log to a log linear model, right? Because there I've got the same Y variable. So there, if I see a higher adjusted R squared, that model would be preferred to the other. I can also compare a linear log to a linear model, but I can't compare anything that has a different Y value, right? If I take, I could not do a log linear. I couldn't compare that even to a linear model because the Y variable is not the same, right? That's what matters, right? Because the R squared or the adjusted R squared is the amount of variation I'm explaining in that Y variable. By taking the natural log, I'm inherently changing the variation that would exist. Okay? Yeah.
But for the log and log linear, you can use the adjusted R squared to compare it.
Yep, because my Y variable is the same. So let's say, I don't know if I gave you regression output here. Let's see. So I don't have one here. Let's just for a second assume that this second model I ran was a log model, just for the sake of the argument, right? What could I actually compare? So there's actually two things I could use to see which of these models is better. Now, this isn't the case here, but like I said, let's just assume that these results were for a log model just for the sake of this example. Well, because I now have the same, I don't want a log. What was this? I need to have, let's assume we've got, I think this will be helpful. So this will be a good thought experiment. So I've just got the regular linear model. Well, I can compare them because I've got the same Y variable. So what would I look at? Which one has a higher adjusted R squared? So if this was the results for a linear model, what would I say? The adjusted R squared is higher, so this would be the preferred model. Now, these two things won't always go hand in hand because we have different levels of statistical significance, and we really aren't identifying any statistical significance just by looking at if the adjusted R squared is higher. We were just kind of looking at a directional change there. What's the second thing I could look at to determine if that second regression better fits the relationship between rent and average income? So I would probably start out with, what does the test statistic lead to? P-value, right? So I would probably want to look at the p-value first. Which one is going to have higher statistical significance? Whichever model has a lower p-value, okay? And hold on real quick. I'm getting paranoid. Okay, I did start this recording. All right, so does it have a higher or lower? P-value looks like it's 0 in both. I have a problem. So if I can't look at the p-value because they're both really small, which one of them is going to be more statistically significant? Well, if I have a higher test statistic, what's happening to the area to the right? It's getting smaller. So it will have, I could actually tell you which of these has a lower p-value. Which model here has a lower p-value for that X variable? The one that has a higher test statistic. So if this was the linear output, the linear model that using the linear term of income would actually have higher statistical significance, right? I would actually say it's preferred, not only because the adjusted R squared was higher, but also the coefficient estimate that I have for that linear model is having a higher test statistic, which inherently means the p-value is small, right? It has higher levels of statistical significance. Now, what can happen, once again, not always the case, but I would be aware that those two things don't always match. You could technically have, especially if I add in additional controls, I could technically have a higher adjusted R squared, but this p-value could actually become larger. So they might suggest different models. Those two things won't always line up. They are highly correlated, right? But in terms of will they always be true, not necessarily the case. Okay. So just so you're not, if I ask you for two things that would either support or don't support the use of the linear model, you can identify the adjusted R squared and you should be looking at the p-value of that test statistic, but they may suggest different models. That is possible. In this case, they both suggest to use the linear model.
So what do you say if they don't line up? What's the
The question I would ask you is, what are two statistics that would suggest the use of or not the use of each model? So you would just tell me the one supports the use of the linear model, the other one would support the use of the log linear or linear log, whatever we're looking at, right? So you would just kind of state both of those conditions and which models they would suggest. Is that?
Yeah.
Did I see another hand? So I'm just talking about that. No? Okay. Any other questions on this one before we... Yeah? Different question? We can keep moving.
Yeah, so one thing I had on some of the questions, I was just kind of looking for something to talk about for interpreting things when comparing models. And I'd go to looking at the difference between R squared and adjusted R squared. So I'm wondering when that is appropriate. It wasn't really on the answer sheet.
For comparing different models?
Yeah, I might be using it wrong.
You're okay.
Just like if the difference between the R squared and adjusted R squared is bigger for one model than the other.
So we didn't quite dive into those issues, and I wouldn't give you one where I ask you to identify the model based off that difference. The situations where that would apply, let's think about it will be good because it'll connect to concepts that might pop up on the exam. When would the gap between the R squared and adjusted R squared, if I was comparing models, when will the R squared always be the same? If I've included the exact same number of variables. So if I was comparing linear log to log linear models and I've included the same number of controls, having a higher adjusted R squared, I know that the gap between the R squared and higher adjusted R squared might always go down, right? But really, it would have to be looking at like a squared model there, in which case I really can't look at the gap between the R squared and adjusted R squared. Because when I start to include interaction terms or squared or cubed terms, what automatically is going to happen to my R squared? Well, if I'm including squared terms interactions, it's just like I'm including more variables. So my R squared would always go up. Okay? Now, that's where we kind of say we really just default to looking at that adjusted R squared. Okay? Now, the gap in between the two, there is a way we could use that to then determine, but I won't expect you to kind of be able to use the gap in between the two to make any decisions, right? When we're comparing models of interaction terms or quadratic models, you simply can say which one has the higher adjusted R squared. Okay? And then in some situations, if we have the same number of controls, like log linear, we can't really look at the R squared because it could potentially be the same, right? Because even if we add in more variables and it's less explanatory, well, that's going to decrease R squared. But the fact that we added more variables in increases it. You could see R squared stay the same when in fact it's not as good of a model, right? So that's where we kind of default to just looking at the adjusted R squared. Is that? Okay. Any other questions people have they want to kind of see work through here? This is why we're here. It's the time to ask. Yeah.
Did you go through questions 20 and 21?
Yeah, so that's good. We should probably do some.
As 21.
Should probably do some instrumental variable stuff here. Is that what this is looking at? Say 20 and 21?
Yeah.
Okay, so this is fixed effect stuff, right? So I'm trying to predict GDP with all these additional controls. And I also include fixed effects from guessing this is the country. So here, yeah, fixed effects, country level fixed effects, okay? So one thing I would think about, even for 19, just the few that I graded, the interpretation from fixed effects models, you need to add in something to your interpretation, right? So if I was interpreting beta 4 here, so that's my R&D, and let's just think, I don't know how it's measured. Let's just say it's an additional $1 into research and development, right? It might be thousands or something like that. For every $1 additional invested into research and development, the predicted GDP of a country goes up by $29, approximately. But what else do I need to add into that interpretation? Holding everything else in the regression constant. Whereas when we're looking at fixed effects models, what we need to add there is holding constant net trade, health expenditure, and population. But by using fixed effects, what am I actually controlling for? Anything that is time invariant within a country, right? Whatever I've included fixed effects for, that's what I'm controlling for the time invariant factors specific to that thing. So if I had an example where I instead was looking at universities and I had university fixed effects, it's holding constant anything that's time invariant about that university. Okay? So if I'm interpreting a coefficient from a fixed effects model, I need to add in that to my interpretation. That I'm holding constant the time invariant factors specific to whatever that fixed effect was. In his case, specific to that country. Okay. Any questions on that before I keep moving to your other questions?
So does time invariant mean that it just doesn't change over time?
It means that in this example, the United States has shocks that look similar across the 10-year time period, and Afghanistan might have shocks that look similar across the 10, right? They're constant over that time period. Okay? Now, this is where I alluded to a little bit last class. What if I didn't do country fixed effects here, but I did year fixed effects? It's a little bit weird, right? Because when I include year fixed effects, well, I'm no longer thinking about things that are time invariant. However, my panel data is set up, so here it was country and year. If I control for the year, it would be anything that is country invariant, right? So it would be things within the same time period, the thing I included fixed effects for, that doesn't vary across countries. What example did I use last class for this? If I look at the last 10 years, what is something that impacted all countries? COVID, right? It impacted every country, right, within that time period, right? And it was a shock in that year that impacted all countries, right? So that would be if we included year fixed effects. So there, it's not time invariance, it would be country invariance, right? It doesn't vary across the countries within those time frames.
How would that work then?
Well, in terms of the regression output that I give you, I would set my panel data set up instead of by country and year. I would set up by year and country. I'd use the same FE command, but what it would do is essentially include a dummy variable instead of for every single country. It would just include a dummy variable for every single year. That's really what we're doing there with fixed effects. So the output would look basically the same, right? It would here. It's just that I'd be setting it up differently in my panel data set so that it included year fixed effects as opposed to time. And I would tell you in the problem, right? Here I'm telling you it's country fixed effects. I would change this to instead year fixed effects. So you know what the fixed effects that's being included is. Another question.
Can you explain that one more time with the difference between fixed effects for year and fixed effects for country?
Yeah, if I include country fixed effects, so I know I had something like this written out last class, but we can do this again here. So if I'm thinking about whatever I include my fixed effects for, right? So if I include country, state, county, individual, whatever this fixed effects is, panel data sets are across subjects and time, right? So whatever I include fixed effects for, if it was the country level here, it would be the other thing. So time, I didn't include fixed effects for, right? So there it's time invariant factors within a country. If I instead include time fixed effects, or in our case, this would be years, right? It's going to be anything that is country invariant factors. So it doesn't vary across countries within not the same country, but within the same whatever I included fixed effects for, right? So the thing that is invariant is what I didn't include the fixed effects for. And then it's that they're invariant within whatever I did include that fixed effect for. Okay. And these could change, obviously. I could do universities and month, or I could do states and days, right? It's just time periods and then kind of some type of subject level, right? Country, state, even individuals if I wanted to. Right? So didn't forget about your original question. You said 20 and 21. So I think we kind of touched on 20, right? So we got that one. But 21, let's assume we're concerned with autocorrelation in our error term. All right? So we're testing for autocorrelation in our error term. Which of the following do we need to run to get our residuals and then regress those in our lag residuals? So this is kind of more of a definitional thing. Might be something good. If I was writing a cheat sheet, maybe to have this written down. So when we looked at a first difference regression, a fixed effect regression, or we demean those variables, all three of those should produce the same exact coefficient, right? They're all different ways of including fixed effects. Okay? However, when you test for autocorrelation in your error term, what you're saying is, does the kind of year-to-year changes in that error, are they correlated with the previous year-to-year changes? So when we were looking for that autocorrelation, we were always looking at a first difference regression, right? So what we were doing there is thinking about if I were to take YIT minus YI T minus 1, right? I'm looking at that first difference now of the X variable from its previous time period, right? And then I was essentially kind of saving those error terms, right? I would save those error terms and then regress those on the lagged error terms. That told me whether or not I have autocorrelation in those errors. And what's kind of happening there, not to get too lost in the weeds because it's not going to be as important for the exam, but notice if I have my change, right? What would kind of the change in my errors be? Well, if I run those on the lagged change, I actually end up with what? T minus 1. But over here, I would have the error term from the previous time period minus the error term from the second lagged. So it's kind of like this cancels out, and I'm seeing is there autocorrelation in my errors across this time, or across these time periods. But the answer is that in order to run that test for autocorrelation, I have to be looking at these first difference regressions. If I were instead to ask you a different question, which is which of these three would produce the exact same coefficient estimate, it would be these first three. Instrumental variables, although it can solve my omitted variable bias problem, right? It won't necessarily give me the exact same estimates as using fixed effects to resolve the omitted variable bias problem, right? However, first differences, demeaning, fixed effects would all produce the exact same coefficient estimate. There are three ways of doing the same thing. Now, in practice, and this is kind of something I also started to see missed on that 6 problem set. I don't think I have an output here. So let's say, and I'll get to part B in a second. Let's say I gave you the fixed effects regression here, right? I'm telling you that should give you the same size estimate, say on research and development, as if I did a first difference regression. I should still see the coefficient on research and development is 29.35. However, if I use a first difference regression, what is going to be different about that coefficient estimate? So even if on average, I were to see the same size of the coefficient, by looking at a first difference, if I look at the very first time period, can I calculate a first difference? So if the first year in the data set is 1990, can I take 1990 minus 1989? No, I don't have 19. So what's going to happen to that very first observation or first year observation for every country? I'm going to lose it. So if I use the approach of using the first difference, what's going to happen to my sample size? So if I lose the first observation from every country, it's going to go down. So this goes back to, once again, not a cumulative exam, but if I think about when I'm calculating a test statistic, it's the coefficient estimate I see, could be from these fixed effects regressions, divided by the standard error, which we're going to have something up here, and it was kind of like n minus k minus 1, right? Well, if when I run this instead of a fixed effects regression, I run a first difference, right? We said, on average, I'm going to see the same coefficient from either regression. But I know that my sample size when I use first differences is now going to be smaller. So what's going to happen? What does this denominator represent? The standard error of that coefficient estimate. So my standard error, if the denominator is smaller, the standard error is going to get larger. If this denominator is larger, my test statistic gets smaller. If my test statistic gets smaller, my p-value gets higher, right? In which case it's going to be less likely I can reject the null, or I lose statistical significance by using that first difference approach. That could be a question I ask, right? So what happens to the size of my coefficient estimate if instead I use the first difference approach? Size doesn't change, right? We're on average going to see the exact same estimate. It's controlling for those time invariant factors, right? However, because I have a smaller sample size, it could change the statistical significance, increasing the p-value, lowering the test statistic, or making it less statistically significant, okay? Any questions on this idea? Okay. So we still have part B, which we haven't answered yet. So if I was looking at this test for autocorrelation, and I haven't graded enough of them, I didn't see a lot of mistakes, so this is a common mistake, but in the past, I've seen this be a common mistake. So if I gave you the output where I use the first difference regression, I obtain the residuals and lag residuals, I include this no constant, which was part of what we had talked about, but that's not going to be anything I ask you about in the exam to trip you up. I'm going to always include it for you and show you the results of this autocorrelation test. Are my residuals correlated with those lag residuals? Well, if I look at this p-value, when I run a regression, I'm always comparing to the assumed true value of what? 0. When I run the test for autocorrelation, I actually need to be testing against not 0, but negative 0.5. So I won't use the p-value for my regression. I need to test it not against 0. I need to test it against negative 0.5, right? So we kind of forget about this, but if we go back to the very beginning of the semester when we were talking about means, when we talk about test statistics, it's taking the statistic you see, now subtracting the assumed true value and dividing by the standard error. Well, in almost everything we do with regression, we're assuming this is equal to 0. With a test for autocorrelation, we're assuming that that autocorrelation, it's not technically, that's a coefficient, we're testing against negative 0.5. So we don't want to simply look at the statistical significance from that regression. We want to look at the statistical significance of that test against not 0, but against negative 0.5, right? In which case, this is statistically significant at every single level. If you incorrectly use the p-value where you test against 0, what levels would you say it's statistically significant? None of them. So it can lead to very different decisions, right? So if you're given output like this, what tells you about the statistical significance of whether or not there is autocorrelation or error term is that p-value from that test against the value of negative 0.5. Okay. Any questions on that idea before we keep? Okay with that? Yeah.
Could you go over a little bit on how d-means variable regressions control for omitted variables?
For the sake of just review and time, just know that they are doing the same thing. So I can give you an intuitive explanation as to why. What does a fixed effect for countries do? It controls for anything that across time is on average the same for that country. So if I calculate the average of all my variables for each country, what is that doing? It's controlling for the average across time for that one specific country, for anything that wouldn't vary across time. So that's why d-meaning would provide us with the exact same results, right? It's going to capture every single factor across this time period that on average is the same for this country. And that's why it provides the same results as kind of fixed effects. There's like, a long mathematical proof that you can use to show this. But ultimately all you need to worry about for the exam is that they would provide the same size coefficient. And in fact, one advantage of the d-meaning, right, is what should happen to the statistical significance. Well, do I lose any observations there? No. So I actually end up with not only the same size coefficient as a fixed effects regression, I would also end up with the same statistical significance. So those two things should give me the exact same results. Yep. Okay. So what's something maybe we haven't went through yet? Since you're here, I'll give you kind of advantage on the exam. So I might ask you something kind of similar to this on the exam. So let's say I've got 24 and 25 here, all right? Well, let's see, what do I have up here? Yeah, we'll use this one. I'll be more specific so I can kind of use some more general terms, right? So let's say I've got this very basic kind of regression where I want to predict unemployment rates based off of whether or not, I think this was marijuana usage, right? So, I think that maybe whether or not it was legalized in the state might be a good instrument. So what would my first and second stage regression be? So I know we can use the IV regress command, but we want to understand what it's doing. And we also might need to use the behind the scenes stuff when we're actually determining, is it a good instrument, right? So if I had unemployment and I'm trying to predict the relationship between unemployment and marijuana usage, right? So my first stage regression is going to be, I take, excuse me, whatever my X variable is. So in this case, it's kind of marijuana usage. And here, I should write these instead of betas, kind of represents a different one. And I will use as a predictor, right, my instrument. So here, this was kind of whether or not the state had it legalized, right? Now, if I'm wanting to include additional controls, I can, right? Now, if I include additional controls, I need to make sure that they're in both this first stage and eventually in my second stage. So when I'm writing ... here, this could be controlling for the individual's income, what state they live in even. You can kind of combine, we won't, but you can combine fixed effects with instrumental variables, any controls you want. So this is kind of our first stage regression, okay? So first stage regression is right here. There are then two things we can look at to determine if the first criteria is going to be met for a good instrument. So the first criteria for a good instrument is that kind of this expected value of X given different values for the instrument, right, is something other than 0. Or said differently, is that covariance between X and our instrument, does it exist, right? Is there a relationship between X and our instrument, or is that instrument endogenous to X, right? Is it correlated with it? Okay. So from a first stage regression, what are two things that we would look at? The first one should hopefully be easy. I can always simply just look at there's a general rule of thumb to see from that first stage if it's a good instrument. It's if my F statistic is greater than, it's a nice easy number to remember, 10, right? Now, the second thing I would look at, if I did have kind of my first stage regression output, right? would be not just the F statistic. So this is a different example, but I could look at my F statistic. I would then also look at the instrument that I used, and I would look at its p-value. Okay. So for us, the second thing I would look at is the p-value of my instrument from that first stage regression, is it less than, and we could make this decision at any of our conventional levels, right? 99, 95, 99%. Now, similar to when we were talking earlier about model comparison, these two things, although highly correlated, will not always suggest the same thing. So I could end up with an example, and I think actually on the problem set, one of the problems, this was the case. You could end up with an F statistic of, say, 13, which is greater than 10, but you could end up having a p-value on your instrument of 0.15, which wouldn't quite be statistically significant at any of our conventional levels. They can both suggest the same thing, that it is a good instrument, but it's not guaranteed, right? They can't. So once again, I would ask you, what are two statistics that support the first criteria of endogeneity for a good instrument? And what would they suggest? Is it a good instrument or not? Well, if the F statistic here was greater than 10, that would suggest, yes, it is a good instrument. But the fact that the p-value is below 0.1 or 90%, we couldn't actually say that there's any relationship or that the instrument is endogenous to X at any of our conventional levels. So we can have one of these statistics support the use that this is a good instrument, and the other one could be that it's not. Okay. Now they both might suggest that it's a good instrument, or at least in terms of that first criteria. Okay. Any questions on this? Yeah.
So you want the instrument to be endogenous to X or to Y?
It needs to be correlated with X, right? So that covariance or the correlation of X and the instrument needs to be something other than 0, which would mean it's endogenous. Endogenous means it plays a role, right, in our model, or the instrument plays a role in predicting X.
Then don't you have to rerun the first regression but add in the instrument?
Yeah. So this was just our first stage, right? So here, maybe I should, these were like to see if that first condition was met. So this was like my first stage of the regression that I had to run for an IB. My second stage, right, I'm actually going to look at what my Y variable is, right? I'm trying to now predict that Y variable. Instead of using the actual values for X, I will now, from my first stage regression, predict those X values, right? And instead of using the actual X values, I will include the predicted X values and all of my additional controls. So in that second stage, what is not included? You don't include the instrument, right? The only thing that you're using the instrument for is to come up with your first stage results, which then help you come up with predicted values of that X variable, okay? So in my second stage, it looks just like my regular regression, but instead of using the actual values of the variable I instrumented for, I use the predicted values from my first stage, okay? Excuse me. All right. Yeah.
So on the actual test, when it said, if it says like write out your first and second stage regression, are we writing out the code for that, or are we just writing the?
You're writing a regression,
okay.
Right? So you would write out this regression for the first stage. This is going to be my second stage, right? I'm adding things in other than what the question asks because I might ask them on the final, right? So this would just be my first and second stage regression. Using the first stage results is how we kind of saw, is that first criteria of a good instrument that it is endogenous to X, is that met? Now we have a second criteria for a good instrument. So here I couldn't obtain a statistic that supports the second criteria from my first or second stage, but I can run an additional regression that we talked about. I could give you the output for that tells you whether or not that second stage is met, right? Or I could ask you for what would be a regression you could run to support the second criteria of a good instrument. So if the first criteria was that the instrument was endogenous to X, the second criteria is that the expected value of Y given the instrument, or we could think about this differently as the covariance between Y and your instrument, that it is exogenous to Y. So if it's exogenous, it's not related. The covariance should be 0, right? So for that second criteria to be met, our instrument needs to be uncorrelated with Y. It needed to be correlated with our X variable, but uncorrelated with Y. So what's a regression I could run to kind of look at this? Well, first of all, I could just look at the covariance, right? But the covariance, I don't have any like statistical, so I don't have any p-values associated with that. So we said, what could you do? You could run a regression where you look at your Y variable. You then include your X variable, but you also include the instrument, and you can include your additional controls as well, right? So now what this is doing is saying, even controlling for marijuana usage, what would tell me whether or not there's a correlation between Y and my instrument? Beta 2, right? What would tell me whether or not that relationship or that coefficient is anything different from 0? I would simply look at the p-value associated with the coefficient on my instrument, right? If it's, what do I actually want this p-value to be? This is a weird scenario. So let's say I run this regression and the p-value on my instrument is, well, here, which is a better one, 0.07. And a lot of the time we're like, oh, this is a good thing. I can reject the null, right? But what would this actually mean? Well, if this p-value is, if that's less than my alpha of 0.1, at the 90% confidence level, what am I actually saying? There is a correlation between the instrument and my Y variable. What do I want? No correlation. So what do I actually want to do, right? In order to see if the second criteria is met, I actually, from this regression, want to be able to fail to reject. I want that coefficient to be equal to 0, right? So here I would actually want to see p-values that are high in order for that second criteria to be met, or that the instrument is exogenous to Y, okay? So I went a little bit more in depth than what the question asked. It just wanted the first and second stage regression, but I could ask you about what statistics from the first stage would support the first criteria of a good instrument. And I then might ask you what's a hypothetical regression you could run and what statistic from that regression would tell you if the second criteria is met. You would run a regression where you look at the same Y variable, but you include X and the instrument. And then you would look at that p-value on the instrument. And if for the criteria to be met, you actually want that p-value to not be small, because that means you reject the null and you reject that it's equal to 0. You want it to be equal to 0 for that second criteria. You want it to be uncorrelated with Y. So from that hypothetical second regression, you actually want to look at that instrument's coefficient and hopefully has a p-value that is greater than 0.1. And then we could fail to reject at every single statistical significance level that we have.
So if it is correlated, then you just wouldn't want to use it.
It just doesn't meet our second criteria, right? So in order to be like an optimal or a good instrument, we would actually want both these criteria to be met, right? If it fails one of them, it's not a good instrument. Okay. Any other questions here? What was the second question here, just to make sure? I'm sure I've answered it, hopefully, at this point. So I could also just ask you for just general intuition, right? I would probably go a little more in depth on the exam than these questions did. But if I want to think about why would the state level policy meet the 2 criteria? Well, I can look at the first stage results, right? But if I just wanted to give an intuitive explanation, the decision to legalize marijuana, what does it need to be for that first criteria to be met? It needs to be endogenous to marijuana usage. Do you think when a state legalizes marijuana, usage goes up or down? Yeah, it has a huge impact. It goes way up, right? So it's endogenous, meets the first criteria. Now, the state level policy on legalizing marijuana, do you think that's correlated or uncorrelated with unemployment rates? There, I would grade you based off of the explanation that you give me. If you tell me that you believe states are making these policies because they just care about revenue, then maybe it's not correlated with the unemployment rate, right? They're making the decision for a completely unrelated reason to unemployment. But what's a story that would actually say that second criteria is like not valid? Well, that would mean that unemployment rates and the decision to legalize marijuana were correlated. If I had high unemployment rates, what might I be less likely to do? I mean, I might be a little stereotypical here. I don't think this is a crazy example. If unemployment is high, would I be more or less likely to want to legalize marijuana as a state?
Less likely.
Probably less likely, right? Not saying that everybody is less productive. I know I am if I'm using marijuana, right? So to legalize it, right? I'm guessing, right? If unemployment's already high, I don't want my populace to be even more likely to become unemployed, right? So there could be this connection between the two here. That second criteria might not be met. Okay. Right. Any other questions that people wanted to see kind of work through here? Yeah.
I have a question on any of these, but I remember on the midterm, we've had a couple of questions asking like why we do certain things. Will there be any questions like that on the exam?
You have to be a little more specific. Why we do certain things.
Like, for example, I think a lot of times, like the midterm had a question on like why we do why we test for multi-purpose multilinearity or something like that. Do we ever have a question of
Oh. I think I know what you're referencing, and I think there's going to be one somewhere up here. It might not have been, it might be like an old quiz question. Let me see here. So, so if I think about like when I'm using fixed effects, I think what you're referencing is one of the assumptions we have in all of our regressions is that the expected value of our error term, given the X values that we've included, is equal to 0. So if there's anything that we've omitted from the regression that is included in our error, it potentially means that the correlation with the variables we included, that expected error won't be 0, right? If there are things specific to in this example, let's use my cigarette use one, all right? So if I think that I've omitted some important variables, which might be, I don't know, the cigarette tax of the state, right? Well, what would cigarette taxes do? Make it more or less likely I use cigarettes. Well, it increases the price. If we know anything about economics, prices go up, people use less, right? And so there, that cigarette tax, if I omit it, it likely is going to impact Y, but it also, right, if I have higher or lower taxes, if that's somehow correlated with any of my other X variables, now in this case, maybe it's not, right? In which case it's okay that it's omitted. But let's say one of my other controls I had in there was, well, really income, probably cigarette taxes. If states have higher taxes on average, what's going to have to be true if people can like freely move across states? If prices are higher in a state, in order for people to want to live there, what's also going to end up being higher? Income, right? So states that have more taxes, likely those taxes would impact cigarette tax would impact cigarette use, but it would also impact the income in that state. If I run this regression, the expected value of my error term is not going to be, given these values for X, would not be equal to 0. So what's one way I can kind of correct for that? Well, if there's things specific to a state that don't vary across time, what could I include? What would control for time invariant factors within a state if I used state level fixed effects? Then I get rid of those omitted variables. I no longer have that bias, and now the expected value of my error term, given these different X values, goes back to 0. I'd be less likely to kind of ask something like that, but I think that's what you might be referencing. Okay. Trying to think what we did on Tuesday. If there was anything else that we didn't get to. Yeah, there's another one that might be good to review here. So, which I don't think we talked about Tuesday, and we should probably talk about now. So let's say I have this regression, and I did a linear Y value here. I could do the same thing if I had the natural log of rent, right? So in this case, I'm trying to choose between, should I include a linear relationship between rent and income and population, or should I choose a linear log, right? I could do the same thing with choosing between a log linear and a log log, right? So I could give you a slightly different example, we could do the same thing. So if I'm testing for whether or not I should be taking the natural log of multiple variables, what I'll do is I'll include both the linear terms and the natural log or the nonlinear terms. Okay? If I've included these here, what model, if I had to choose, gun to my head, should I choose the linear or linear log model? Well, I gave you a joint significance test for these two variables. Okay? So I did a joint significance test for using the natural log term. Okay? The p-value associated with that is 0.36. Okay? So when I run this test for whether or not I should be including these two natural log terms, can I say that they're statistically different from zero? If the p-value is 0.36, what levels? I always start out assuming that those coefficients are equal to zero. So would I be able to reject that? My p-value is 0.36. Is that going to be less than 0.1, 0.05, or 0.01? So at any of my conventional levels, can I say that I should be including those natural log terms? No, which would suggest what? I shouldn't be using the linear log model. I should be using the linear model, right? So that would be one reason why I should choose the linear model here.
Did you look at the p-values too to like figure that out?
I could also then say, okay, that's one statistical reason or support for why I should be using the linear model. What's another reason why, and although this won't always be good, this is a good example where we really should rely simply on that joint significance test. Because if I try to use the p-values of these coefficients, well, if I'm running a joint significance test, right, I'm not choosing like different relationships for different variables. I want to know, should I just have just the linear terms or just the natural log terms of these two variables? Well, what's true about the statistical significance of the natural log of income compared to just using a linear term? It is less statistically significant. But what's true about population compared to the natural log of population? Natural log of population is actually more statistical. Still, both are statistically significant, but this one is less, right? The p-value is smaller. So here, I actually can't make a decision using those p-values because for one variable, it looks like maybe it's better to do linear. One looks like it's linear log. Here, when we run a joint hypothesis test, we're saying, should I run this as simply linear for both variables or linear log for both variables? In which case, we won't look at the individual statistical significance of each variable. We're looking at the statistical significance from that joint hypothesis test, right? Whether both of those natural log terms, can we say that they're statistically different from zero? Here we can't, which means we shouldn't be including them and we should just use those linear terms. If I ran the same regression, but I did a joint significance test for the linear variables, what do you think would likely be the case about the p-value I see? Probably smaller, because if this suggests I shouldn't be using the natural log terms, a joint hypothesis test for the linear terms should be suggesting that I use those. So the p-value, it might not meet our threshold. Technically, it might not fall far enough to be below 0.1, but it is going to be smaller, right? And we have these weird scenarios where sometimes we end up with p-values for both joint significance tests where neither one meets our thresholds. But we would note here it's likely that that joint significance test for the linear terms is going to be smaller than 0.36, right? Does it go all the way to be below 0.1, 0.05, or we don't really know, right? But here I'm not even asking you that far, right? I'm just asking you what model should you choose based off of this joint hypothesis test. Okay. Now I can do a very similar thing in question 5. I could include both a squared and a cubed term, okay? If I run a joint significance test, so here I'm trying to predict the number of arrests with unemployment, but I included a squared and a cubed term. So here, if I run a joint significance test for the squared and cubed term, what is that telling me? That's testing against whether both of them should be included at the same time. So really, what am I comparing the cubed model to here? If both of these terms weren't included, what would I be back to? Just a simple linear model. So I can't compare using a joint significance test. I can't compare the cubed model to the squared model, but I can compare it to the linear model, right? So here with a p-value of 0.14, does that suggest that I should be including both the squared and cubed term? No. It would actually suggest that the linear model is preferred to the cubed model. Now that's one statistical support for why I should be using the linear model. What is another one that I could use in this example? But here's where it gets a little bit tricky because it won't always necessarily line up depending on if, because here I'm just comparing to the linear, right? I'm kind of skipping over the just including the squared term. What else would tell me that these squared and cubed terms shouldn't be included here? Not just the joint significance test, but if I look at each of those variables, what's true about both of their p-values?
Super high.
They're very high. So can I say that the cube or square term, even just on their own, are any different from zero? No. If they're no different from zero, if I think about this regression, well, my coefficient is zero. It doesn't matter what the square or cube term is. Anything times zero would be zero. They're not helpful in making my predictions for unemployment. Or sorry, number of arrests here. Change the example. Okay. So when I run this joint significance test for the squared and cube term, I can really only compare that to the linear model. Okay. Now, if I go back here, if I wanted to compare it to the squared model, will the joint significance test tell me anything? No. It only tells me if I'm comparing to that linear model. But if I wanted to compare the squared to the cubed model, what statistic would I look at? If I don't know, always, when I'm doing model comparison, always default to my adjusted R squared. Now, we talked about the one example where that doesn't work earlier today, which is if my Y variables aren't the same, right? So there is one caveat to that. I need the Y variables to be the same. But when I'm looking at interaction terms or squared models, they mostly default to the adjusted R squared. So which model has a higher adjusted R squared here? This is 0.0368, 0.0364. The squared model actually has a slightly higher adjusted R squared. Now, if I were to look at these R squared values, what's true about the R squared from both of these regressions, both the squared and the cubed model? Here, if I asked you which one's larger, you can tell me which one is larger. They include the same controls. So they include the same controls, but what have I included? One additional variable. So what has to happen to the R squared? Even though to the fourth decimal it looks the same, I know that the R squared from the model where I included the cube term has to be higher. Okay. So I could ask you a question like that in the exam, giving you very similar output, and I'm doing this with my face for a reason. All right. So even though you can't determine there's a difference between the R squared, knowing the concept that when you include an additional variable, that the R squared has to be higher, as long as we've kept the other number of controls the same, even if it doesn't look like the fourth decimal, you know the one that has more variables has to be higher. Now, for the adjusted R squared, that doesn't apply, right? And so in this case, the adjusted R squared tells us, make sure you're using that squared model. What would also be another statistical reason that would kind of support we shouldn't include the cube term? All I would have to do is look at the individual statistical significance of the cube term, right? Not even close. I mean, p-value 0.95, that's, I couldn't like fabricate data to get a p-value that high, I don't think, right? So we definitely shouldn't be using the cube term here. And kind of another interesting thing to point out, if I include a cube term when I shouldn't be, what can happen? And this is why I don't want to rely on the individual statistical significance of the squared term and the cube term on their own. When comparing to the linear model, I want to use this joint significance test, because when I include the cube term, what did it do to the statistical significance of my squared term? If I just had the linear and squared term, it looks like the squared term should be included, right? When I include the cube term, it now makes it look like it shouldn't, right? So I can't use these results, right, to then say that the squared term should not be included. All I can do is use these results to say whether simultaneously the cubed and squared term should be included compared to the linear model. And if I want to compare the cubed model to the squared model, that's where we look at the adjusted R squared and the statistical significance on the cube term. So here we've said, let's use the squared model. I could then go one step further. Should the squared model be preferred to the linear model? Well, now what would I want to compare? Adjusted R squared. Did my adjusted R squared go up or down? Looks like it went up, right? So I should use that squared model. Now, here would not be a reason that would get points if I asked you, what is a statistic that supports the use of the squared model? But the R squared is higher. It is, but it should be higher. We've included another variable essentially, right? So that does not support that I should include the squared term. The adjusted R squared being higher supports the use of the squared included. Wow. Supports the inclusion of the squared term. And then an additional piece of statistical information that would support the use of a squared term compared to the linear model would be what? That it's statistically significant at my 90, 95, or 10 and 5% significance levels, right?
Can you go over question 17?
So we're running out of time here, but we can probably go through this pretty quick here. Yeah, so this is one where the formula sheet might actually be helpful. So we said, I think we went through one kind of similar to this last class. If I give you the measurement, if I tell you that a variable has measurement error in it, and then tell you what the variance of that measurement error is, and I tell you the variance on the variable that has the measurement error, right? So this would simply be, I think it was like 36 and 4. So I just be plugging those values in.
Okay.
When we have measurement error, what will always be true about the coefficient estimate we see from our regression compared to what the actual coefficient is. So I might ask a question and phrase it this way. If I have it, instead of calculating kind of what that coefficient would be, you could also just tell me the directional change. Right? So if I have any measurement error, first of all, variances are always positive. If I take a number and I divide it by a number plus a positive amount, this fraction will always be less than 1 or decimal, right? So the actual coefficient would be multiplied by something less than 1. So the coefficient estimate I see for my regression, if the variable has measurement error, will always be too small, or what we called attenuation bias. It's attenuating it towards 0. Okay. So I said another way I could ask this question is if I gave you the regression output, what do you have from this formula? You know the variance. Where is it at? There it is. The variance in the variable, the variance in the measurement error. Do you have beta 1 or beta 1 hat? If you have the regression output, you actually have the predicted value of beta 1. So the estimate you see from the regression output, that is kind of beta 1 hat, right? That's the estimate you see. The actual effect would be, right, whatever that coefficient estimate you see was, so what, 0.117 divided by whatever this fraction is, right? And if you divide by something that's less than 1, then the estimate should actually be a little bit higher. So I could kind of ask you to kind of tell me what that coefficient should be if you didn't have the measurement error as well. That would be another kind of way I could phrase that question. All right. All right, so we have a couple minutes. Any other kind of last minute logistical questions about the exam or anything we're kind of wondering about that we've been too shy to say up to this point? Okay. So you have that cheat sheet. I would kind of use that almost as like a study tool. As I'm going through things, I would jot things down that I want to put on there. I have things that trip me up to kind of make sure I'm remembering this. The format to the question earlier will look very similar to this, right? So even though you have things written down, I'm probably less likely to ask you about like certain like specific conditions that you could have written down here, and more of how do I use data output or regression output to actually then answer those questions, right? So, but in terms of the format of the exam, it'll look very similar to this, right? I'll kind of have a couple questions that'll be related to some output. They kind of build on each other until there's a point maybe where then I kind of switch over topics. I change kind of the example that we're looking at. Next 4 or 5 questions are kind of all related to those same variables. Switch over. So you'll probably get 4 to 5 kind of different like examples on the exam with about 4 or 5 questions associated with each one. Any other questions for me? I'll let you guys get out of here. So I'll tell you right now, so I won't unfortunately be in my office on Monday, so I won't have in-person office hours. Look for an announcement on Canvas. I think I'll have virtual office hours in the afternoon. You have some last minute questions. If you email me Tuesday morning, I likely am not going to be free enough to keep checking my email to get fast responses out. So get me questions that you have sooner rather than later. If you get them to me some point on Monday, I should be able to get you a response before the exam. But if you wait until the day of the exam, I can't promise I'm going to be able to respond to your email before we actually meet for the exam based off of different meetings I have in the morning. I know how available I will be. I'm just going to look at my email and respond. Okay. Any other? Okay. Well, good luck with the rest of your finals. Good luck studying, and I will see you guys in this class on Tuesday.